slides, and we'll kick off talking about how distribution networks are smoothing the road ahead for increased DER connections. So as I said, my name's Mark Sprawson. I'm from EA Technology. I lead EA Technology's Insights business, which supplies consultancy services and software products to network operators all around the world. And we cover these four key areas that are shown on the screen now. Everything from understanding the energy future, thinking about the transition towards net zero and new business models for networks, right through to understanding asset management and ISO 55001 compliance and making the best asset management investment decisions for all stakeholders. So clearly today's webinar is going to focus more on these two items on the left-hand side, which is all about decarbonisation and about sort of integration of distributed energy resources, particularly EVs, but other DER as well. So let's start with setting the scene, and why is this such an important topic for us just at present? Well, obviously, in order to achieve our goals with regard to decarbonising transport, say, we're going to have to provide a large number of connection points to the grid. These can be at large hubs, but increasingly we're going to have to see these connecting to the low voltage network, domestic or street level. Now, the LV network obviously has finite capacity, and when this capacity is exceeded, the life expectancy of those assets reduces. That will increase the chance of sustained long-term damage, and without intervention, we risk potentially building a much larger network than we really need, which will require extensive disruption and huge levels of investment. So in order to get the most out of the LV network, there are two things that are becoming more and more of a necessity, and those are modelling and monitoring. Modelling is important clearly to show where the capacity exists and for increasing sharing of that data with key stakeholders to help them make informed decisions. Monitoring looks in detail at how demand moves on a daily, weekly or monthly basis in order to allow the network to operate up to, but not beyond its limit. Once the utility has established a model, it can not only be used to ascertain where there might be network constraints today, but it can be a powerful tool in analysing scenarios based on changing customer profiles and new uptakes of technology, such as electric vehicles in the future, and provide an indication of future hotspots where investment is likely to be needed. But beyond these internal uses, many network companies are beginning to share a version of this model with their customers via web portals. And why would they do this? Well, it allows customers to understand available capacity and to self-serve their connection requests for, say, building a new property or connecting a new charge point to the network. And they can receive a quote for that connection in a matter of minutes, rather than by submitting an application, waiting days or weeks for the response. So this not only improves customer satisfaction, but also reduces the burden on the connections department within the electricity utility. And key to making this a success is presenting the complex engineering that lies in the background in a simple and intuitive format for users to understand and engage with. So in this webinar, I'm going to explain how several electricity companies in the UK have achieved this, and we'll show examples of live systems that allow customers to interact and share information with the utility to inform better decision making and improve customer service. So have we started to see an increase in DER connections yet? Well, in some cases, we certainly have. If we take the example here in Australia of solar PV and behind the meter battery storage. But on the demand side, so for EVs, for example, we're yet to see a significant uptake here, but it is coming. The charts on this slide show scenarios from CSIRO. And it can be seen that in the more aggressive scenarios, which now align with AEMO's ISP view, we're looking at approximately 1 million EVs connecting per year from the late 2020s through to 2040. So will the current systems and processes that we have for managing connections be able to cope with this upsurge in volume? And how does this picture compare with that in other nations? So for example, the UK, which has a more aggressive stance with respect to electric vehicles, given the shorter timescales that it's imposed for the ban on internal combustion engine cars, 2030. So in the UK, we're actually seeing a very similar trend or similar projection. On the left chart here, we see the EV uptake projections for cars, and on the right for vans. And we can see an expectation in a number of scenarios, which are now being favoured by some observers, of 11 million EVs by 2030 and 30 million by 2040. So that means if you follow the kind of gradient of that curve, that we're seeing around 2 million EVs connecting per year, or double the rate that we just saw in the Australian example. But bear in mind that the UK's population is more than double that of Australia. So on a per capita basis, we're actually pretty much aligned. So, as I said, are our current connection processes fit for purpose? And if they're not, how are DNOs adapting and changing these to fit this upsurge in particularly electric vehicle connections? So the main challenge with the existing connections process for many electricity companies is that it was conceived and implemented in a time when the volume of connections was small, and it's not easily scalable to meet the demands going forward. The original way of managing connections was to have customers provide some information, historically via paper forms and then migrating to online submissions, which would then be assessed by a connections technician or an engineer. However, the customer had no real idea of the level of available capacity, and hence the likelihood of a cost-effective connection being possible before they submitted these forms and received the quotation. So the knock-on effect of that is that if a customer receives a quote which is too expensive, they may choose to resubmit a slightly different connection application, maybe varying the amount of capacity requested slightly, or even choosing to connect in a slightly different location if possible. This would then require a repeat of the original assessment to be performed by the electricity company. This got to the state in the UK where some customers would actually submit multiple connection requests with slightly different details, forcing the electricity company, who in this case can't actually charge for these assessments, to perform numerous studies and analyses in the full knowledge that only one of these was ever likely to progress, probably the cheapest one. So what if this burden of finding the cheapest and easiest connection option was reversed, such that it could fall to the customer rather than to the electricity company? Why would the customer want this? Well, if they could find out where the cheapest connection is possible in a quick and intuitive way, rather than waiting for all of the assessments to come back from the electrical utility, that would be advantageous for them. If we could take a process that lasts weeks and make it last minutes, that would surely improve the customer experience. And that brings us on to the idea of self-serve connections. So I'm going to look a little bit now at the connections journey and look at how it might evolve. So in these graphics that I'm going to show here, any items that are coloured in purple are the responsibility of the customer, whereas those that are coloured in blue are the responsibility of the electricity utility, or DNO. So in the traditional connections approach, as I said, customer completes an application form. This might be paper-based or web-based, and it's then submitted to the DNO. When that happens, the study will then be performed by the DNO, usually via a connections technician or perhaps an LV designer. They'll then issue a budget estimate to the customer for how this connection could take place. And if the customer is satisfied with that budget estimate, they then move on to requesting a formal quotation. And this involves a much more detailed analysis being performed. Network model would be built, and then a series of studies such as load flow, voltage drop, and earth loop impedance assessments would be carried out, determining a connection cost and then issuing this out to the customer. So as you can see, there's more blue than purple in this process. So the large portion of the burden of responsibility for activity falls squarely on the utility rather than on the customer. It's also the case that a number of parallel studies for different connection options could well be conducted, and a large number of those would result in abortive work. So how could we change this and move forward to a self-serve view of the world? So here, instead of filling in a form and submitting it to the electricity utility for consideration, that same information is input directly into the connections estimator. The customer then can receive their own budget estimate within a matter of minutes. Crucially, if they choose to, they can rerun this assessment as many times as they like, varying the details such as capacity and location before the utility needs to actually get involved. Once the customer has a scheme with which they're happy, they can then submit that to the utility for a formal quote. At this point, all the details and the cost estimation are loaded up by the connections technician, who's already got that information at their fingertips, and then checks them and performs any additional analysis that might be required. They can then issue the formal quote to the customer. So what we've achieved here is the same endpoint via a much shorter route in terms of the amount of effort that's required within the utility. And this type of system is live now and has been for 2 years in the Autodesign tool, which is used by Northern Power Grid in the UK. So we'll have a quick look at that now, and I'll show you a quick video explaining what this system does and how it operates. So Northern Power Grid, it's worth mentioning, are a distribution network operator in the UK who have around 4 million customers. So this video, when it comes up, will show you their website. So we'll start on their website and you'll be able to see the process as we go. So this is showing Northern Power Grid's website here, and a user would click on the Get Connected section, and they would then scroll down and choose the budget estimate auto design option. Go to auto design. There's various guidance as we go through, explaining to a customer what the tool can be used for and what it can't be used for. So what type of loads, how many new houses, say, or new connections, and then the customer goes through to use auto design. The first bit of information they will then need to enter is an address for the works of the connection. So here we see someone entering a postcode and populating an address associated with that postcode. There's then a number of questions that are walked through, such as, are any additional works other than a new connection required? What type of connection is it? A new house, an EV charger? So here we've chosen a house with non-electric heating and with EV charging facilities. And there's then the option to include some detail around how many houses or chargers, say, we're looking at installing. This is summarized here for the user to check that they are happy, that the details are all correct, and if they are, they then proceed to the next stage. There's some messages and information around how the data will be used to ensure that the user is happy going forward, and then we move on to the main map screen. So this map is centered on the address chosen by the user, and what you can see is all of the low voltage cables and overhead lines within Northern Power Grid's network, coded green, amber and red, where green shows the connection that you are looking at as a customer is possible, red where it's not possible, and amber where it may be. The user then is guided via a series of help instructions to draw on the site boundary for where their connection is going to take place. So this is, let's say, the plot of land we've acquired for our infill development of 3 houses. We then connect from our plot of land to the nearest electrical assets, which are green, i.e. ones that can take our connection. We then confirm we're happy to proceed, and we are presented with the system showing us the actual quote for how much this will cost. And you can see there it says the estimated price, £20,500 plus tax. A full copy of the connection estimate is then sent by email to the user, and I'll show a copy here of the letter that will be sent as a PDF. And you can see here it gives the details of the budget estimate that's been produced, tells you what the property is, EV charging, etc., what the load is you'll be allowed to have, and then indicates the price of works. There's then a series of pages going through all the details around that budget estimate and explaining what's required. So hopefully you can see from that that it's a fairly simple, straightforward way for a user to actually engage with the system. It's important to note that there are some data gaps, as there are in any network, and some of the amber areas that were shown in the video are those areas where there's imperfect data available. What's important is to press ahead with that imperfect data and refine as we go, rather than wait for the data to be absolutely perfect. The data is continually being improved and new versions of it are regularly uploaded, allowing the calculations to be performed quickly against these pre-processed set of results. So what's the value of this approach to the network company? So let's have a look at some numbers. We spoke to a number of electricity companies in the UK about their connection request data. And we found that of all of the connection inquiries that they receive and that they generate budget estimates for, approximately 40% of those do not then progress past the budget estimate stage. Now, this could be because the customer receives a figure which is far in excess of their available budget, because it's one of several duplicate requests that I mentioned earlier, or the scheme is quickly abandoned for some other reason. That means that around 60% of the inquiries obviously do generate a formal quote. But of those, it's actually only, well, around 2/3 of those do not actually become accepted. So in other words, another 40% of the total connection inquiries get as far as a formal quote being issued, but then don't result in a connection, meaning of course that around about 20% actually lead to completed connections, so 1 in 5. In some areas of the UK, and for some certain connection types, this number is actually quite a lot lower. 1 in 8 or 1 in 10 has been reported. So if we stick with our 20% figure, this suggests that as a minimum, around about 80% of the time spent by the connections technicians and planners looking at LV connections is actually abortive. And while this may have been an acceptable level in the past when connections volumes were not so high, as these volumes increase and the pressures on staff time become greater, it's unfeasible to continue at this attrition rate. So how do these numbers stack up in a bit more detail? So again, we look there at the volume of connections. So here we looked, again, with some electrical utilities in the UK, at the length of time spent on connection requests. So what we found was that on average per license area, and just for context, England, Scotland and Wales is split up into 14 different distribution network license areas. Current connection volumes are around about 8,000 per license per year. And to do the budget estimate process takes between 1 and 1.5 hours per application. But remember from earlier that 40% of applications stop at this stage. So if 40% of those are abortive, that actually adds up to 3,200 hours of wasted time per license area per year. Now, those that progress to a formal quote, the companies we spoke to said that it takes something like 3 to 3.5 hours to actually produce that formal quote following on from the budget estimate. And again, the majority of these do not yield an actual connection. So if 2/3 of those formal quotes are abortive, that results in a further 9,600 hours per year being lost. So if you add up all that wasted time of the budget estimates and then the formal quotes, you get to something like 13,000 hours per year of abortive work per license area, which is equivalent to around 7 to 8 full-time staff working on that. And that's just at today's connection volumes. Now, if the use of a self-serve approach could drive even half of the inquiries via that route, then clearly the savings are enormous. Going forward, one electricity company who we spoke to, who actually operates across 2 license areas in Great Britain, has told us that over the next regulatory period, which is set to run from 2023 to 28, they're expecting per license area 800 connection requests per day. So that will require a team of 100 technicians per license area just to process the budget estimate portion of that. Now, clearly, that is an unsustainable business model going forward as these volumes increase. And what we need to have is more automation in the system as per the self-serve approach that I showed a moment ago. But it's not just about self-serving connections that this type of approach can be useful for. There's also a drive in the industry to make data available and more transparent for informed decision-making for all stakeholders. So network companies have been looking at how they can do this and better communicate future capacity to customers. This becomes increasingly important in a world where planning the electricity network means taking into consideration a whole range of factors that were previously not required. For example, the worlds of transport planning and electrical planning were in the past quite separate, but they're growing ever closer together as the electrification of transport gathers pace. So what does this mean in practice? Well, an example of this, again from the UK, is the Charge project, which is an £8.5 million multi-year project, or about 15 million Australian dollars. This is investigating a number of areas, including looking at charging arrangements for electric vehicles that don't have access to off-street parking, and the greater use of flexible managed charging at such shared locations. One of the key outputs from the project is a software tool known as Connect More. And this tool uses electrical network modeling and transport modeling to overlay these different elements and show the need and indeed optimum locations for charge points going forward. The tool is available now. It's live on the website of the network company who is conducting the charge experiment, charge project, SP Energy Networks, and there's a link to it at the bottom of this slide. So let's take a very brief look at the system. So I'll show a brief video again of the heat map for Connect More. And as I said, this features two main layers, one which is electrical capacity and one which is transport. At the electrical layer. So this video shows a section of the network in SP Energy Networks license area, which covers parts of the northwest of England, serving around about 1.5 million customers. And the user can choose to look at LV or HV. We've chosen LV here, and each of these dots in green, amber, and red is a distribution transformer. And the amount of load we're looking to connect, which is being scrolled through on the right from 25 up to 150 kVA, is then run against the background levels of capacity there are to see whether there is indeed capacity. And if it's red, there is not, and if it's green, then there is capacity for that kind of connection. A user can then zoom in to a particular location that they're interested in, and they can then see, as they could for the Autodesign system earlier, the LV cables and overhead lines for that particular locality. And it will then enable them to understand whether they're likely to be able to connect their EV charge point, say, to that particular location. So here we zoom in to get down to street level, and we can see some transformers here, some of which are green, some of which are amber, and then we can see the cables coming out of those transformers, which in this case are red because we're choosing to connect 150 kVA. As we reduce that down, we see some of them go green or amber, showing that connection is possible or may be possible at these individual locations. Clicking on the HV toggle at the top right then allows a user to look at the higher voltage network capacity in the area. So by HV here in this particular location, we mean 6.6 kV and 11 kV. And again, the same sort of process can be followed, scrolling through from 250 kVA worth of connection up to 2.5 MVA. So that's a way of sharing what the capacity is in the network at the moment. We can then also look, as I mentioned, at the transport layer, and we can try and understand what's the likely demand going to be for EV charging in different areas of the network as we move forward in time. So here again at the top right, there are some options to select regarding the type of charging that we're interested in, be that home charging, workplace charging, destination charging, or indeed en route charging on the various main roads of the transport infrastructure system. Once we're happy with our selection, we can then move forward, and we can then select whether we want to look at a high uptake scenario for EVs or a low uptake scenario, and whether we want to consider sparse or plentiful levels of charging infrastructure. Finally, we select a year that we're interested in moving forward, anytime from now through to 2050, and the map then updates and is color coded to show the levels of EV demand that there are likely to be in these different areas. By clicking on one of these areas, lots of information around it is brought up in the sidebar, showing the levels of EV demand and charging that are needed, or indeed by clicking on an item on the road there, as you saw at the close of that video. So why is this important for us going forward? So this is important because it again allows us to bring together the worlds of network planning and transport planning. And it allows us to overlay those two things on top of each other so we can see where the demand for EV charging is going to be greatest and where the levels of capacity are available to either facilitate that or where upgrades are needed. So in my last few slides, I'll just go back to look again at the sort of journey that we're making here. So sharing better data for decision making, we looked at the traditional connections journey at the top, and then we looked at the self-serve or auto-design approach in the middle. What we can see if we look at what Connect More is doing is that it's somewhat different. So it's primarily, initially at least, a tool to help inform decision making amongst key users. And those users could be charge point operators, organizations with significant portfolios of buildings and assets who want to understand where best to site their charge points, or local councils trying to understand where to position public charging infrastructure going forward. We mentioned that it shows the higher voltage as well as the low voltage. And going forward, it's shortly going to be offering connection estimate functionality, as we saw in Autodesign. The new version of that tool that's going live within the next couple of months will allow customers in that particular area to obtain connection estimates. Crucially, it's playing a role now as a starting point for those who are looking to set out local energy plans, which is a very hot topic in the UK at the moment, as local councils seek to identify the lowest cost way to achieve decarbonisation. It also allows them to, say, look at the HV as well as the LV and understand what sort of costs might be needed to transform the electricity network going forward. And it's facilitating greater levels of collaborative dialogue between the network company and its stakeholders. So in conclusion then, what are some of the key actions currently being taken by network operators in readiness for the significant increase in LV connections? Well, a large number of companies in the UK are already offering some form of self-serve for connections on their website. Some are fairly rudimentary and some are more advanced. And about half of the companies are doing this now. But by the end of this year, almost all of them have committed to having some form of functionality in place. The sharing of data and information regarding network demands now and into the future is a growing and key part of the net zero transition at a local level. And this is being actively encouraged by government and regulator in the UK. Customer perceptions are changing, and they do not want to have to wait days or weeks to find out about costs and availability for connecting their charge point. If we think about other examples from other elements of life, we think about the move towards self-serve in retail or in travel, where we now self-serve our check-in and baggage tags, etc. at the airport. We think about how quickly these become the norm and supplant the existing model. And there is every indication that the same is happening now with connections moving forward. By implementing self-serve approaches, the network companies are able to save staff time and hence money. But it's important to note this isn't about cutting jobs. It's about making the business scalable and sustainable into the future. It also improves customer satisfaction as the turnaround times are dramatically reduced. And sharing data in this way is helping network companies become part of the wider conversation regarding optimal pathways towards net zero, and leads to them being viewed as an enabler rather than a potential barrier to any decarbonisation ambitions. Thank you very much for your time today. I'll happily address any questions that have come through while I've been speaking now. For anyone who's interested in looking more closely at these approaches or having a follow-up discussion, I will be attending this week the Energy Networks conference here in Brisbane along with my colleagues. So if you're around, please do feel free to come and have a chat. Otherwise, my contact details are on the slides, which will be made available after this session as well. So thank you very much for your time.
First question, Mark. Is the hosting capacity calculation behind Connect more looking at current amps limitations or also looking at voltage limitations?
Yeah, so that's a great question, and the answer is it looks at both. So it looks at load, it also looks at volt drop as calculated via a load flow engine at LV.
Okay. Next question is, what is the uptake of something like the Autodesign? How receptive are the public to going into the self-serve model?
Yeah, absolutely. So we're starting to see the uptake increase, as you would expect, as connection volumes also increase. So what we are seeing is that initially it may have been quite small, but going from now, what we're seeing is around about 50 to 60 users, something of that nature, per week on the Autodesign system. So obviously, if we scale that up across the course of a year, you're looking at 2,500 to 3,000 Autodesign studies being performed and taken through. And as I mentioned in the presentation, we're currently sitting at around about 8,000 connection applications per license area per year. So we're obviously sitting around about 30% of those, it looks like, are now maybe going through the Autodesign route. And we envisage that will continue to grow as we move forward.
Okay. Next question. They're coming in thick and fast now. Can you provide any details on what criteria make the network appear green versus red? What limits are being considered?
Yeah, so it's the same as sort of answer as I said before. So there's essentially a bunch of load flow and voltage drop and earth loop impedance assessments are done and are then stored in the background. And what that does is it works out for each portion of network exactly how much additional load could be connected before any of those limits are breached. So if it works out that there's 27 kVA worth of load that could be connected there, it then just, if a customer asks for 25 kVA, it will appear as being green. If a customer asks for 30, it will appear as being red. So it just, basically that data is refreshed on a regular basis and is then dumped back into the system that faces the customers. Usually that refresh is happening about once every 2 to 3 weeks, that kind of level. There's ambitions to make that go faster so as to ensure that it's updated with the latest information regarding the new connections that have come in.
Okay. Next one, in the UK standards, is voltage rise measured differently to voltage drop?
No, so is it measured differently? So the UK standard is to have plus 10% on voltage rise and minus 6% on voltage drop, and those are the limits that are respected within any of these self-serve systems.
Do we know how large an undertaking developing an LV heat map is in terms of time and cost?
So clearly the answer to that question will depend on what sort of level of data you currently have in the LV network that you're considering. But what I would say is that, you know, there's some approaches that have been now trialed and tested and developed and are quite mature from these UK experiences. So essentially the challenge is more about just mapping the LV data that you've got against that system. So it's really just, it becomes more of a data integration problem. And as long as the LV data is stored, is digitized and is stored in some coherent manner, usually using something like common information model or something similar, it's actually very, very possible for it to go through. I mean, the Autodesign, to give some examples, I guess, the Autodesign system was built in around about 12 months. And that was obviously the first system of its kind. So other systems that have been built since have been done more quickly than this. And it'd probably be a matter, say, of doing the data integration, probably a few months worth of work, depending on how much is actually required. If the data is very good and is very clear and there's not many data errors within it, it could be significantly faster.
You may have touched on this. How does the model collect data? Can it read the information from GIS or other modeling systems? Yeah,
so it's basically say there's different approaches available, but usually it's a case of getting something in kind of STIM compatible format, something like that, and then integrating it such that the model then can communicate with it appropriately. But so there's lots of different systems out there, and it's basically it's about just finding the right communication technique to however your LV data is currently housed.
Okay, next. In the self-serve application process, what options are available for the customer if they wish to connect where there is no available capacity?
So if the customer goes on and basically all the area around them is red, then what happens is there's a pop-up that comes up that suggests that what they should do is contact their network operator and have a discussion. So sort of take them out of the self-serve process at that point and go back to a more conventional route, because what the system doesn't know is what upgrades might be coming in a few months' time anyway, and also what the system doesn't do, it doesn't provide the option for connecting to something that is red, whereby a reinforcement would be triggered. And it's quite possible that that may be the quickest way for that customer to get connected. It's just that they would have to think about the costs that they might have to bear for some upgrades to the LV network as appropriate.
Okay, there's two from the same people, so I'm going to combine. Is SynCal or another modeling engine used in the background, and are the models HV/LV models?
Yeah, so there is a modeling engine that's running in the background. So in the background of Autodesign, the modeling engine that's used is one that's based on something called Debut, which is a UK modeling engine that's been used by the electricity companies for many decades. And it's basically a new version of that, which has been used for this implementation. In the case of Connect More, that's also using the Debut engine, which has been sort of rebadged, if you like, as Connect going forward for the LV. And for the 6.6 11 kV, it's using an engine called IPSA, which again is an engine that's used by a number of network operators in the UK and around the world. And it's also using OpenDSS, which is an open source and fairly well-known engine. There's no reason why you couldn't use any other engine. It's just a case of, to do that, you've got to, again, make the systems talk to each other. So the systems are basically being configured using this Debut or Connect, IPSA and OpenDSS as the three current engines within there. So they're probably the ones of choice for quickest implementation.
I think we got one other here, but I'm not 100% sure what it means, because if we were starting from scratch for the LV network, and then that's it.
So it might be a question around sort of the length of time required, or the amount of effort. Probably the other thing that I should mention that I didn't touch on earlier was around sort of the level of accuracy that's obtained here as well. So Northern Power Grid, with their Autodesign system, have obviously tested this extensively. They were the first movers in the UK, and as far as we know, the world on this. And the level of accuracy they're obtaining for their quotations that are being generated is 95%. So they're very happy with that. And what that has actually led them to do is to move on to the next stage. So the next generation of Autodesign that's going live in, I think it's about 6 to 8 weeks time from now, is actually going to allow a customer to go through not just a budget quotation, but actually all the way through to formal quotation as well. So they'll actually be able to go through the process and have something that is a formal offer, a binding offer from the network company, without the network company actually having to do all those detailed studies themselves. So that's clearly taking that journey that I showed in the kind of the purple and blue segments even further, and sort of rebalancing it more towards the customer than the network operator. And indeed, there's a sort of vision to go even further in the future, and maybe use this as this sort of sole source of truth, if you like, for connections, and generate design drawings and so on that can then be taken to site, all from the one system. So it's definitely something that's being built around moving forward. Okay,
Joseph's come in and has said, can it assess all loads in DER, reverse power flow and effects?
So there's the engines that basically perform those studies absolutely can. So Connect or Debut and IPSA and OpenDSS can all do reverse power flow as well. The current systems that are online for Autodesign at Northern Power Grid's request only cater for demand connections. There's no reason why it couldn't do reverse power flow and generation. It's just they're the specific connections that they're trying to sort of prioritize through this route at this point in time. But the system technically is absolutely capable of doing bidirectional.
So sort of following on from that, in Autodesign in amber or red areas, is somebody considering giving options for customers like batteries?
So it's a good point. It's possible that, so in areas where it is amber, if for example you were looking to put in some EV charge points, there's been some talk around whether some sort of flexible options could be used for managed charging within those areas, say, or some sort of different contractual negotiations that could take place around time of use tariffs, and so using batteries to maybe back off at certain times of day, etc., etc. None of that is currently in the system, but they're all areas that are currently being explored, and I imagine will probably form future innovation activity in this space before then going into BAU. So it's worth saying Autodesign is now in business as usual from being an innovation project. Connect More is now business as usual live on SP Energy Networks websites. Other companies tend to have some more innovative approaches that are not quite live yet on BAU, but they will be, as I said earlier, by the end of this year.
Good job, Mark. I think we're coming to the end.
Yeah, I think
we have any other questions popping up.
I think we're about 1 minute from time as well, aren't we? Something like that. So I think all that remains then would be for me to say thank you very much to everyone for your time, and say anyone who's around at the Brisbane conference this week, very happy to have a conversation. Elsewise, I'm sure my team will be making these slides available to you, so you can reach out via the contact details there. But thanks very much.